During the development of a powerful spacecraft, it is inevitable to encounter some errors, whether few or many. We cannot assert with 100% certainty that a rocket will be perfect from its first launch. Starship is a prime example. Despite its size and status as the most powerful rocket in the world, it has experienced issues during both testing and launch phases. This is not by chance. All of Starship's tests, even the ones that ended in explosions, achieved their intended objectives. SpaceX has adopted a different approach to rocket development known as rapid iteration. This involves building prototypes, testing them until they fail, addressing any issues that arise, and then building a new prototype to repeat the process. This development process for Starship has proven to be extremely effective. So effective, in fact, that although Blue Origin has been around longer than SpaceX, it has yet to achieve a single orbital launch. Meanwhile, SpaceX has repeatedly done so with the Falcon 9 and even with Starship, having completed 4 launches, with the third and fourth launches reaching orbit and even landing in a designated area in the sea. The progress is evident, but it is still not complete. SpaceX must continue testing to fully realize the potential that Starship is being celebrated for. After the 4th Starship test flight, SpaceX and Elon Musk identified additional issues that need solutions to ensure the flights can meet their ambitious goals in the near future. First and foremost is the issue with the heat shield tiles. These are protective tiles that shield the spacecraft from the extreme temperatures during re-entry to Earth, playing a crucial role in Starship's reusability and human carrying capability. However, in the re-entry video of the spacecraft, it was seen that many heat shield tiles failed to perform their task, with several falling off and breaking apart. After all, SpaceX and Elon Musk have come up with a solution for this. The development of Starship's heat shield demonstrates SpaceX's commitment to continuous improvement. Initially, this system included about 18,000 heat shield tiles made from aluminum and silica fibers with various shapes, especially around the nose cone. These tiles were attached to the spacecraft's body using pins with a layer of white insulating material underneath that disperses the heat before it reaches the metal part of the spacecraft. Recently, SpaceX has made some significant changes on Ship 30. They started removing some of the heat shield tiles to add a layer of ablative metal, replacing the white insulation layer. They will then install new heat shield tiles that are twice as durable as the original ones. This ablative material is only placed in areas that experience the highest temperatures during re-entry. Notably, this ablative material is not reusable and may need to be replaced after each flight. This is considered a temporary solution and will be improved in future flights. However, for now, SpaceX is prioritizing other aspects of the Starship program. These improvements show that SpaceX is continually seeking ways to optimize the performance and safety of Starship, demonstrating flexibility in adjusting the design based on data and experience from previous test flights. Another issue that is no less important than the heat shield, which most of us might have overlooked, is the matter of the flaps. During the 4th flight, it was discovered that the position of Starship's flaps was not conducive to the spacecraft's heating process. SpaceX and Elon Musk have a solution for this. But first, you must understand the differences in the flaps of this giant spacecraft. As explained by Elon Musk in a live interview with YouTuber Everyday Astronaut, when Starship re-enters the atmosphere from low orbit, it typically returns with an empty cargo bay. Due to the center of gravity being at the rear engine section, the spacecraft naturally wants to flip engine first. To control the angle of attack, Starship uses a complex fin control system. The aft flap plays a primary role in controlling the pitch angle of the spacecraft. When extended, the aft flap increases drag and pushes the tail of the spacecraft up, helping to maintain an angle of attack of about 65 to 70 degrees relative to the ground. This prevents the engines from facing directly into the hot airflow. Meanwhile, the forward flaps have a secondary role. They are mainly used to adjust roll and fine-tune the pitch angle. When fully retracted, the forward flaps minimize frontal drag, preventing the spacecraft from being pushed backward. The interaction between the flaps is very complex. All four flaps influence each other and contribute to the control of the spacecraft. However, during high temperature reentry, the air is typically very stable and uniform. This means if the spacecraft operates correctly, the flaps will only need to move minimally to maintain the desired angle of attack. As the spacecraft descends lower into the atmosphere, where there's more turbulence, the control system will need to work more actively to cope with changing conditions. However, during the fourth flight, the flaps oscillated relatively strongly at the beginning of the heating process, indicating an abnormality not accounted for in initial calculations. To address this issue, engineers propose moving the forward flaps further back to the straighter part of the body and adjusting flap positions to be more leeward to minimize turbulence. Notably, for the upcoming fifth flight, SpaceX plans to test a type of movable seal, possibly a flexible fabric tube inserted into the gap, to maintain a tight seal when the flaps move. These improvements are not only aimed at optimizing airflow and thermal efficiency during atmospheric reentry, but also demonstrate SpaceX's commitment to continuously improving Starship's design based on data and experience from previous flights, working towards the goal of developing a fully reusable and efficient spacecraft. The next issue during the flight was with the engines. In Flight 2, the engines consecutively failed after the two stages separated, causing B9 to explode mid-air. In Flight 3, when B10 was nearing its destination, the landing engine failed, leading to the booster explosion. In the latest flight, one engine failed after takeoff and another during landing. Fortunately, the landing process still went smoothly, marking the first time the Starship stages landed successfully. So what caused these issues? In SpaceX's update on Flight 3's problems, they stated that the booster's filter was blocked in the liquid oxygen tank, preventing a fuel from reaching the engine. In a recent Everyday Astronaut video, Elon Musk explained this in detail. Specifically, he revealed that ice caused the blockage. So why did ice appear? Starship's fuel includes liquid oxygen and liquid methane. When the fuels burn, they produce water and carbon dioxide. The freezing point of carbon dioxide is quite high, around minus 57 degrees Celsius or negative 70 degrees Fahrenheit. Water, as we know, freezes at 0 degrees Celsius plus 32 Fahrenheit. In the extremely low temperature environment of liquid fuel, these substances easily freeze, causing blockages in the pipes. This revelation indeed clarified Starship's problem. So what's the solution to this? First, to address the blockage issue caused by carbon dioxide and water ice, Elon Musk mentioned adding a component he referred to as an ice strainer or ice catcher. While it's hard to visualize what this part looks like and how it works, it will be interesting to see how it functions in practice. Next, Elon Musk also mentioned upgrading the valve system, specifically using multiple parallel valve systems. This will double the valve's reliability. If one line fails, the engine can still operate on the other line. This ensures that the engine continues to function well, allowing the rocket to maintain direction even if a valve fails. Another factor Musk emphasized is the pressure during engine startup. In the previous flight, the startup pressure was quite low. Next time, they'll increase this pressure, making engine startup more reliable and reducing the need for all engines to ignite simultaneously. In addition to these internal improvements, the overall design will also change. In the future, parts such as bolts, flanges, and gaskets will be removed and replaced with welds. This will reduce weight, increase reliability, and decrease the risk of leaks. To enhance the engine's capabilities, SpaceX will also add an integrated cooling system and a secondary cooling system. These additions will help the engine withstand extreme re-entry temperatures without the need for heat shields. These are great improvements, and I hope they'll be implemented soon, perhaps even on the next flight. At the end of July 2024, SpaceX is expected to conduct the next significant test flight of Starship. This fifth flight will use Ship 30 as the upper stage and Booster 12 as the booster stage. The objective is not only to test the improved heat shield, but also to verify the effectiveness of several other critical systems, such as the stable operation of the flap system and the Raptor engine system. The lessons learned from this effort will bring us closer to the goal of creating a fully reusable rocket, opening the door to the future of space travel. If you are interested in advancements in the space industry and want to stay updated on the latest developments, follow our channel. With SpaceX leading the way, the future of space exploration is wide open and full of promise. As we know, Starship, Elon's most colossal rocket, might advance to newer versions like Starship V2 or Starship V3, with an upgraded height being a certainty. But will their width change as well? How will the fuel tanks be expanded, and how will this affect the rocket's performance? When will the increase in Starship size stop? A future Starship, much larger and more advanced, will travel to other star systems. That is Elon's inspiring promise regarding the redesign of the Starship in a tweet from back in March. The current interplanetary spacecraft has a diameter of 9 meters. SpaceX's Starship, a fully reusable spacecraft designed for missions to Mars and beyond, boasts a current diameter of 9 meters. This significant width, combined with a height of 121 meters, makes Starship the largest rocket ever built. However, Elon Musk and the SpaceX team are not resting on their laurels with this already impressive feat. There are concrete plans to stretch both the Starship and its boosters super heavy, making them taller and thereby increasing their fuel capacity. The primary motivation behind these modifications is to enhance the spacecraft's performance by allowing it to carry more fuel. This would enable longer missions and the ability to transport heavier payloads, crucial for the ambitious goals SpaceX has set for human space exploration. In addition to adjusting the height, Elon has also hinted at the possibility that future versions of Starship could exceed that current diameter of 9 meters. This statement was made by Elon 5 years ago, but given the recent developments in the rocket's length, the possibility of increasing its width cannot be ruled out. Technically, as Starship becomes larger, its fuel tanks also increase significantly. Propellant tanks, which store the fuel and oxidizer necessary for a rocket's journey, are arguably the most crucial components of any launch vehicle. The role of propellant tanks extends beyond mere storage. They directly influence a rocket's efficiency, weight, and overall performance. In the quest for space travel, engineers strive to maximize the amount of fuel a rocket can carry while minimizing the structural mass of the tanks themselves. This is where the shape and size of the tanks become critically important. Cylindrical tanks are the preferred design in rocketry due to their inherent structural efficiency. The cylindrical shape helps to distribute the pressure exerted by the stored propellant evenly across the tank's walls. This distribution reduces the amount of material needed to construct the tank, thereby minimizing its weight. Additionally, cylinders are easy to manufacture and integrate into the overall rocket structure compared to more complex shapes. Increasing the diameter of a rocket can enhance the efficiency of these cylindrical tanks. When the diameter increases, the volume of the cylindrical tank increases faster than the surface area, meaning larger tanks can hold more fuel without proportionally increasing the weight of the tank. This improved volume-to-surface area ratio leads to higher overall efficiency. This means that for a given increase in tank volume, the corresponding increase in surface area, and therefore the amount of material needed, is relatively smaller. Consequently, the tank becomes more efficient, carrying more fuel with only a modest increase in weight. So, which version of the Starship will be the expandable version? It's certainly not Starship V2, as we all saw its first ring earlier this year, and there was no change in width. Therefore, Starship V3, with a height of 150 meters, is likely to be the version that could see an increase in diameter. The first assumption for the change in the rocket's diameter is 12 meters. This number was mentioned in its original design of Starship when it was called the Interplanetary Transport System, or ITS for short. When V3 carries 2,300 tons of propellant, it would benefit from a 12-meter diameter, as this size offers a favorable balance between the volume and the structural materials required. The second assumption for Starship V3 is increasing the diameter to 18 meters, doubling the diameter of its predecessors and aligning with the specifications of Starship 2.0. An 18-meter diameter would make Starship the widest rocket ever built, with the first stage SIC of Saturn V being 10 meters wide and the first stage N1 Block A of the Soviet Union having an impressive diameter of approximately 17 meters at its widest point. Although Elon once acknowledged this assumption, saying probably 18 meters for next-gen system, however, for Starship to operate normally, it would need to increase its height further and have engines either in greater quantity or significantly be more powerful. Therefore, if comparing the two assumptions, a 12-meter diameter would be more suitable for Starship V3. Nonetheless, the possibility that SpaceX might continue to develop another version in the future, possibly V4 or V5, cannot be ruled out. While the benefits of larger diameters are clear, several structural and logistical challenges accompany such designs. The first is structural and transportational challenges. Larger rockets require stronger materials and more sophisticated engineering to ensure structural integrity under the immense pressures and stresses of launch and space travel. Additionally, transporting these enormous structures from the manufacturing site to the launch pad poses significant logistical hurdles. Roads, bridges, other infrastructure may not be designed to handle such oversized cargo, necessitating alternative transport methods such as ships or specially designed transport vehicles. Second is the problem of factory infrastructure speed. Building larger starships will also require substantial upgrades to SpaceX's manufacturing capabilities. The production lines, tooling, and assembly buildings, like those at the Boca Chica facility, must be capable of accommodating the increased dimensions of the new Starship variants. This could involve expanding existing facilities, constructing new buildings, and upgrading machinery to handle larger components. Moreover, launch infrastructure, including launch towers and transporters, will need to be scaled up to support the larger rockets. Finally, there are economical and practical considerations. Beyond the physical challenges, the economic implications of scaling up production must be considered. The costs associated with manufacturing larger rockets, modifying infrastructure, and addressing transportation logistics can be substantial. Balancing these costs with the expected benefits of enhanced mission capabilities is crucial for the viability of larger Starship variants. To be honest, the potential of larger spacecraft is enormous, but it comes with limitations that require SpaceX to make changes or even redesign their entire development program. However, in the end, if SpaceX can create larger rockets, both in height and width, it'll mark the beginning of the peak era of human interplanetary exploration. Putting aside future achievements for the next few centuries, the most important thing is still how far SpaceX has come with the Starship program. SpaceX has made considerable progress in the development of the Starship program after 4 test launches. The most recent test, conducted on June 6th, showed promising results. SpaceX just released an impressive video capturing key moments from this 4th test flight. Starship, the launch system that NASA hopes will return humans to the Moon and eventually take them to Mars, demonstrated outstanding capabilities in this test. The Super Heavy booster performed efficiently in the initial phase of the flight and made a controlled landing in the Gulf of Mexico after separation. The upper part of the Starship also completed its orbital flight before landing in the Indian Ocean, albeit with a small fire. The new video focuses primarily on the journey of the Super Heavy booster. New angles from cameras mounted on the top of the rocket and from a nearby buoy show a spectacular scene as the booster lands vertically on the sea surface. Notably, SpaceX also revealed images of the launch tower at Starbase in South Texas, featuring 2 gigantic robotic arms used to catch the rocket upon landing. At the end of the vehicle, an animation depicts a 400-foot, 122-meter Super Heavy rocket returning to land at the Starship launch tower known as Mechazilla, alongside the words "Next Up" and Flight 5, indicating that the company plans to attempt catching the booster in the next test flight, expected early next month. However, there are still many technical and managerial challenges to be addressed before this can happen. SpaceX aims to catch the Super Heavy on its launch tower so the rocket can be refurbished and relaunched more efficiently and in a shorter time frame, the company says. Elon, the founder of SpaceX, has expressed the ambition to attempt this landing in the next launch. However, Kathy Loiters, the general manager of Starbase, recently shared that this plan might not take place on the 5th flight. Nonetheless, the newly released video shows that this possibility is still being seriously considered. Such a landing would not only create a spectacular sight, but also mark a significant advancement in rocket reusability technology. However, it also poses safety challenges, especially when the booster might carry substantial amounts of residual fuel upon landing. To conduct this test, SpaceX needs to obtain permission from the Federal Aviation Administration to ensure the safety of people and property on the ground. With the necessary procedures, it seems unlikely that the next test flight will happen before August. Overall, SpaceX's recent advances in the Starship program are drawing significant attention from the space community and the public. Successfully developing this launch system not only opens up opportunities for deep space exploration missions, but also has the potential to revolutionize the space industry, helping reduce costs and increase the frequency of space flights in the future. That's all for today's episode. Thank you so much for watching, and see you next time.